Some circuits are tough to wrap your head around because they're just super complex. But then there are the other ones, the ones that are hard to understand because they look way, way too simple. Today, we're diving into one of those clever little puzzles, the charge pump. And this quote just nails it, right? It's one thing to get lost in a massive schematic with 100 parts, but what happens when a circuit with just a few components seems to, break the rules of physics? That's exactly the kind of fun we're getting into today. All right, so here's the big question to kick things off. Let's say you've got a 5-volt power supply, but the chip you need to power requires 10 volts. Your first thought might be, okay, I need a transformer or some kind of fancy boost converter. But what if I told you that you could do it with just a couple of tiny capacitors and some switches? How is that even possible?
Well, that brings us to this really beautiful little piece of engineering, the charge pump voltage doubler. And the absolute star of the show is a component with probably the best name in all of electronics, the flying capacitor.
So what in the world is a charge pump? Honestly, the best way to think about it is like a bucket brigade for electricity. It uses capacitors, which are basically like little rechargeable batteries, to scoop up charge from one place and dump it in another. It's this incredibly clever and simple way to transform a DC voltage. The whole process is this wonderfully simple two-step dance. In phase 1, our flying capacitor gets connected directly across the power supply. So if your supply is, say, 5 volts, the capacitor charges up to exactly 5 volts. It's like filling up our little electric bucket. Easy enough. And now for phase 2. This is where the magic happens. The circuit instantly disconnects that fully charged 5-volt capacitor and reconnects it, but this time it puts it in series with the power supply. So now the capacitor's voltage is literally stacked right on top of the supply's voltage. So what's the end result? You've got the original 5 volts from the power supply plus the 5 volts you stored in that flying capacitor. And boom, you get 10 volts at the output, exactly double what you started with. By switching back and forth between these two phases thousands of times a second, the circuit keeps that 10-volt output steady. Now, you might be thinking, okay, that's a neat little party trick, but I promise you, these things are everywhere. Because they're so small and don't need big clunky magnets, they can be built right onto a silicon chip. They're hiding inside the microcontrollers in your phone, inside op amps. They're even used to create negative voltages, which is a mind bender in itself and something that's totally essential for things like high-end audio equipment. Okay, so we've just seen a really elegant solution. But now, let's flip the script and look at a problem that's way more confusing. What if you want to do the opposite? What if you want to perfectly have a DC voltage? Well, this leads us to what some engineers have called a cursed circuit. And I just love that description, a mildly cursed circuit, because it perfectly captures that feeling of frustration. You look at it, and it feels like it should work. It looks so simple. But the closer you look, the more it just seems to fall apart. It's a total head-scratcher. And this is everyone's first thought, right? I mean, we all learned that 2 resistors in series create a perfect voltage divider. So why wouldn't 2 capacitors do the exact same thing for DC? It seems like it should be the most logical thing in the world. But here's the trap. It all comes down to the fundamental difference between AC and DC. With alternating current, capacitors do have a kind of resistance. It's called reactance, and it lets them divide voltage just fine. But with steady DC, they just charge up once and then stop. They basically become an open switch, blocking any more current from flowing. So what that means is the instant you try to actually use that halved voltage, connect a load to it, all the charge you had stored in that bottom capacitor just drains right out. The voltage plummets to 0, the current stops, and your clever little voltage divider becomes completely, utterly useless. The curse is real. So how do we solve this thing? How do we break the curse? Well, guess who's back? The hero of our first story, the flying capacitor, makes a triumphant return to save the day. And the solution is just as elegant and clever as the voltage doubler. We add a small flying capacitor that just switches back and forth really, really fast between the top capacitor and the bottom capacitor. It's our little charge shuttling bucket brigade again, but this time it's keeping things balanced. So check out this little balancing act. When our load starts draining the bottom capacitor, its voltage starts to dip. The flying capacitor sees this, zips over to the top capacitor, which is still holding plenty of charge, grabs a little bit, and then zips right back down to the bottom one and dumps its charge, topping it back up. This happens thousands of times a second, so the voltage stays perfectly locked in place. I mean, just look at the difference here. It's night and day. Without the flying capacitor, our circuit is a complete dud. The voltage and current just collapse under any load. But with it, the voltage stabilizes perfectly at half the supply, and you can draw a nice, steady current. The cursed circuit has been fixed. It's redeemed.
And this right here, this is the real takeaway. The true genius of this circuit isn't about picking the right values for the capacitors. It doesn't matter. The output is always going to be half the supply voltage because the magic is in the process, that constant dynamic act of shuttling charge back and forth.
So, to quickly recap this whole puzzle, that fly-in capacitor is an incredibly simple but really powerful idea. We saw it elegantly double a voltage, and then we saw it come back and solve that cursed problem of trying to have a DC voltage. It's just a great reminder that in engineering, sometimes the most amazing solutions aren't about the components themselves, but about the clever way you make them dance.
And that kind of leaves me with one last thought for you. We just saw how a simple, everyday capacitor, when used in a really clever way, can do something completely unexpected. And it just makes you wonder, what other simple components, resistors, diodes, transistors, are just sitting there waiting for someone to combine them in a new, maybe even cursed way to achieve something amazing?